Assalamualaikum, my name is NUR AINA AKMAL by TAJUDDIN. We present the final year project 1 about computational fluid dynamics of underwater drone. Firstly is introduction. The remotely operated vehicle ROV is a tiny underwater observation craft that can be controlled from afar. In addition, it is used to provide both work and observation feature in the conjunction with a floating vessel activity. In many ways, an underwater drone is an instrument that is perfect in using for inspection. Mostly, an underwater drone can dive up to 200 meters deep. In order to analyze the dynamic performance of a remotely operated vehicle during a mission such as ship hull inspection, the 6-degree freedom equation of motion must be constructed while a well-modeled hydrodynamic force operating on the ROV is taken into consideration. CFD techniques has recently become popular for analyzing hydrodynamic force operating on a moving underwater vehicle. The goal of this research is to enhance the design of underwater drone chassis by examining the drag coefficient and using computational method to tackle a number of fluid mechanics problems. Underwater drone analysis were carried out by using the ANSYS software, with a voltage and a pressure contour taken into account. Why we should choosing ANSYS software? As the demand to optimize good increase and merging for mistake tighten, ANSYS FD technology provide the opportunity to achieve amazing progress via innovation. Literature review. UUV are classified into two types based on their morphologies and operation: autonomous underwater vehicle and remotely operated underwater vehicle. What are remotely operated vehicle? Which a sort of underwater drone that is a tiny device that can operate autonomously while also being a high-performance configurable ROV. The major goal of ROV development is to ensure human safety on the surface. It causes a lot of pressure underwater when it goes too deep. The second source told that from the 1980 to 1990, there was several failure and successful trials using prototypes in the history of ROV. The era of creating and developing ROV began in the 1990s and latest until 200. The first generation ROV were developed during this time period and achieved the aim of technological advancement. And the third source is ROV are classified into distinct varieties based on their capability and working deep as determined by extensive research and comprehension of a study scenario. The scientists have established that the design requirement and keep them in mind before beginning the underwater drone or ROV design process. Next is problem statement. Drone with the advanced technology may be employed in a number of sectors, such as aerial photography to enjoy nature beauty, where direct human action is difficult, and search and rescue operations for ships buried in the sea, which can be exceedingly dangerous for people. To overcome this obstacle, a new design must be created that can withstand drag coefficient and lift force. Next is underwater drone can have downside such as a difficulty operation in area with a strong water currents and inaccessibility to very shallow oceans. As a result, CFD techniques like continuous rotational motion and spatial spiral motion are being utilized to predict the underwater drone model below the sea training capability. Okay, objective. The objective of this project, firstly, to improve of design underwater drone chassis that looks at the drag force and lift force involving with a drag coefficient. The second is to analyze underwater drone chassis using computational fluid dynamics (CFD). Next is scope and limitation of the project. This research focus on the creation of underwater drone, namely the CSAM underwater drone. What is the purpose of choosing the CSAM underwater drone as the close reference? Because CSAM is the first underwater drone system to combine a wireless autonomous underwater drone with a reliable tether ROV. Other than that, a drone is the most compact design that can be referred. For the limitation, the pressure and the velocity of the underwater drone will be evaluated using CFD during the data collection process. It involves body of the underwater drone which will be designed and tested using ANSYS software. Furthermore, the underwater drone will examine the drag and the lift caused by the vehicle relative motion with the water. The third is methodology. The primary framework of hydrodynamic investigation is guided by governing equation based on the conservation law of fluid physical characteristics, which is mass conservation and energy conservation. The velocity, pressure, and absolute temperature are the three unknowns that must be derived concurrently from these two basic conservation equations. Fluid movement can be studied using either Lagrangian or Lorentz techniques. The formula methodology required for creating the fluid flow experience by the ROV chassis was derived from the analysis aim. There are link elements in the three coordinate axes for the creating tension and motion value, such as the drag force, lift force, and moment value. Next is solution strategy. The underwater drone simulation begins with the creation of 3D dimension underwater drone model, merge link component, and the computational domain for CFD simulation. The figure shows the design of chassis underwater drone. The value of inputting the simulation parameter is the simulation general configuration, fill in the pressure, temperature, depth, and average speed parameter first. The table shows the parameter and the specification of the CFD simulation. For pressure is 1.0 MPa, temperature 32.35 Celsius, the depth is 100 meter, average speed is 2 meter per second, and wall thermal condition is adiabatic wall. Next is starting with the link element, which must set inside the fluid flow of the computational domain proportionate to the computational field of the chassis underwater drone. The figure 2 shows the demonstrate how the underwater drone motion was controlled by illustrating the slope of the underwater drone motion. Next is expected result. The convergent data was shown in this result of the chassis underwater drone because the result was achieved using variable computation and analyzation and boundary condition. It did not alter much. The graph shown that the moment on the z-axis has decent residual value, whereas the force on the y-axis has the least convergence. Underwater drone move related to the fluid flow speed in the horizontal motion simulation, while static underwater drone move at the constant fluid flow speed. As a result, the fluid flow profile on the front of the underwater drone from a stagnation region. The flow tends to diminish from the stationary area for body to the back of the body with a strong profile distinction. The boundary layer is created and it has a smooth gradient between the object surface and the viscosity free zone. Because of the gradient, friction drag is reduced. The figure 7 shows the flow profile of the speed profile. The figure 8 shows the linearity of the drag force value, which is the greater the slope, the more force the underwater drone need to dive. From the graph shown that has a negative linear because the flow velocity direction is normal to the negative z-axis, hence the flow velocity direction is positive. From the table shown that the result of the simulation, which is the drag force from the result get 74.15 Newton, and the lift force is 12.911 kilonewton, and the drag coefficient is 0.91. The growing hydrodynamic features on the underwater drone design are illustrated by the value of drag, pressure distribution, and fluid flow contour from the previous study. Next is appendix. This is my project planning of the FYP1 and FYP2. The first is conduct the background reading, conduct the literature review. The third is specify research planning, and next is conduct the drawing process, perform the data collection and analysis, and then doing the preliminary outcome. On the week 10 is the proposal submission to the supervisor. Next is recording the video presentation, and the last is submission of proposal, logbook, and video presentation of FYP1. For the FYP2, doing the build the prototype, data analysis, simulation, and thesis writing. That's all from me. Thank you.